Okay, yeah, so I think we can get started. So the plan for the panel is we have 40 minutes or so till the end of the workshop. And I have some general topics and questions that I've come up with, but we really do want to have this discussion focus on what is of most interest to the community. So if there are particular topics that our panelists would like to discuss or anyone in the audience, please let me know. The Q&A section, I've opened that up so that if someone posts a topic there, other people in the audience can upvote it so we can see if there's particular things that multiple people would like to hear about. But let's just start. Oh, and one general thing I'll just say, since we've got at least 3 people on the panel right now, let's try not to have each of us speak more than like a minute at a time or something, just so that we can make sure we get everybody's feedback on things. Of course, we can keep going around if there's a longer discussion. Okay, so just to start out with, one of the things that I said at the beginning we'd like this workshop to help with is to foster exchange of ideas between different areas. So one thing I wanted to start with was if there were connections that any of our speakers see between some of the different work they've been doing. We saw today some formalisms for expressing hyperproperties, algorithms for verification and synthesis, and applications. Are there particular connections that sprung to mind as you saw the other speakers' talks that you might like to explore? Anyone want to take the plunge?
I can be the icebreaker.
Okay.
So some of the things that Sanjit talked about. So for instance, fairness, robustness, sensitivity. These are all things that are inherently hyperproperties, and I think that it is very interesting to look into how we can use either the existing work or develop new work to analyze robustness, sensitivity, fairness in the context of AI, machine learning, neural networks. That is something that I'm personally very interested to look into.
Thanks. I had a question related to that too, that maybe we can ask Sanjit your opinion on. I was wondering, what do you think would be needed before we could apply general tools for verification of hyperproperties to these ML verification problems? Right now, you mentioned people have specialized techniques based on optimization, for instance, for finding counterexamples to robustness properties. So no one is trying to formalize that as a hyperproperty and then apply some general hyperproperty reasoning tool. What do you think we as people who are working on, those of us working on hyperproperty verification tools might need to do before that would be possible or would even make sense?
Yeah. So a lot of the examples I gave today were like robustness and fairness. These are hyperproperties, but they've been mainly, a lot of the examples in the ML literature are feed-forward networks. And so these are essentially transformational programs, right? So the techniques that find hyperproperties based on temporal logics are a little bit of an overkill for these, right? The problem is it's a bit closer to the verification of hyperproperties for information flow in transformational programs. So the standard self-composition based approaches and all the optimizations that go with that. So, I think from a verification standpoint, one could try to apply, take the techniques that have been developed for verifying information flow in such programs and then apply it to constructs like neural networks in a manner that is similar to what other neural network verification tools have been doing, right? So that that could be first step. And I have to say I haven't seen a lot of work in that direction. Now, local robustness, though, right? Local robustness is a trace property, right? Because you fix one input, And so you're effectively doing an input-output verification problem. So that's where a lot of the, if you look at the conventional neural network verification work, they've just looked at input-output relations and local robustness. That's where a lot of the work in adversarial ML has been concentrated. So I think if you look at the more general formulations of robustness and things like monotonicity and so forth, that's where I think the hyperproperty verification work comes in to be relevant. I think the other thing is that these techniques, what they have to offer beyond the standard AML methods is that AML methods can find adversarial examples, but in general not be able to prove the absence of them, right? So verification techniques, hyperproperty verification techniques could be used to prove absence of certain kinds of robustness attacks.
Thanks. Anyone else want to add to that?
I think the verification of neural networks is such a hard problem that, even if we don't get to complicated hyper properties, already basic stuff is really at the edge of what we can do. But formalizing these properties is already a very valuable first step, I think. Second of all, even if we can't do verification, then monitoring is certainly interesting. And these statistical types of hyperproperties would be, an ideal basis for the monitoring of intelligent or AI systems. And also, I think going towards synthesis, realizing that the neural network is not the entire system, but you actually build a system around that. And you want to synthesize shields and so forth that then guarantee hyperproperties. That's a really fascinating direction, I think.
Yeah, I agree completely.
One thing I would add to that is I think counterfactual reasoning is actually a hyperproperty, right? So I think that is something that is also of relevance to AI, machine learning algorithms. And in fact, how do you reason about data that isn't there? I think that's also something that is relevant to the verification of AI ML algorithms that could be formalized as a hyperproperty, probabilistic hyperproperty.
So following on.
So one way to I'm sorry.
Go ahead, Borzoo, please.
So one way to deal with this could be statistical model checking, especially for neural networks, where so we did some work which appeared in ICCPS this year, where we wanted to be able to compare the behavior of a neural network to a model predictive controller, and we just wanted to see, how similar they are to each other, right? And whether increasing the number of neurons or the number of layers makes the neural network any closer to the classic MPC implementation. And then, so what we did was we did some sort of statistical reasoning with some confidence to say whether these two are similar to each other, and that can have what we did was for STL, not for hyperproperties, but definitely for the transformation type of problems. At least statistical model checking seems to scale much better when we deal with probabilistic systems. Those issues such as robustness, fairness, maybe there is a way to at least reason about how confident we are for the neural network to provide the output that we expect it to provide.
All right, thanks. So the one question that I had following on from that is, if we can, even if we can formulate some specifications that come up in various application areas, like these fairness properties, for example, or counterfactual reasoning, or et cetera, it may be that they're in one of these very expressive logics where we don't really have much hope of being able to apply general analysis tools. So I wonder if there are any ideas that any of you have based on what you saw today or the work you've seen for classes of hyperproperties that haven't yet been studied. They aren't necessarily natural fragments of one of the logics proposed so far, but that could be important in practice. So for instance, like the monotonicity property that Sanjit mentioned, you could easily encode in any number of these hyperlogics, but it's also a specification of a very particular kind of form. And I wonder if there are classes like that that might be worth studying because they are of sufficient practical interest, even though they might seem like a relatively specific class of formula.
I mean, there are many such classes, of course. But Borzoo, what do you say? Should we make a shameless plug for asynchronous hyperproperties? I think this feels like a
absolutely.
So I think asynchronous hyperproperties are still an understudied class of properties. I mean, there are now a number of proposals how to do that. So we made one where you introduce trajectories and you quantify over the scheduler essentially that regulates how the different traces align to each other. And there is a version of the mu calculus by Marcus Miller-Olm and so forth where you can do that. But the essential problem is that there is no common clock among all the traces that you might want to talk about. And therefore, if you want to have a sensible notion of a hyperproperty over software, say, then you need to deal with this problem that there is no common time step. And even beyond expressing the properties you want, alignments are, of course, incredibly important in order to get simple proofs. It makes a lot of a difference if you force two copies of your system to run in lockstep, or if you run them in a way such that they end up in comparable states at the same time. So there's a lot of leeway in a way where you can play with the alignment in order to massage your problem into one that's easier to verify. And at the same time, the properties become much more general if you go away from this idea that everything is in lockstep. And yet the logics we have don't really cover the space of properties in any sufficient generality. So I think there's a lot of work still to be done.
So one very simple example of that is when you write a program and then you compile it, the compilation introduces multiple steps for each of the instructions. And then if you want to verify that if the compiled program still preserves all the properties or hyperproperties of the original program, then this alignment that Bernd is talking about has to be taken care of. In an intermediate representation or assembly representation, things that happen within 4 steps happen in just 1 step in a C instruction. So that is definitely one of the understudied problems now.
So I think this is a really interesting direction, and perhaps related to this, I mean, I'm not someone who's been working on hyperproperties, core hyperproperties, like some of the rest of you, like Bernd and Borzoo, but I think for an outsider, it would be nice to have a repository of common hyperproperties. Maybe this exists, but I think so. A lot of us see the case safety as there's lots of properties in practice that we encounter that are case safety properties, and so then that tends to be most commonly studied. But I think the hyperproperty world is so much richer than that. So the question here is, what are some of the other sort of real world examples of practical examples, instances of other classes of hyperproperties that you think the community should work on? And can we make this available to the community somewhere, like just maybe create a web page, a listing, some tutorial set documentation of here are all the interesting hyperproperties, right? I think it would be certainly useful to someone like me, probably more broadly useful also.
I think the state of affairs is that these hyperproperties are studied all over the place. They are just usually not called hyperproperties. They're called linearizability, serializability, or maybe common knowledge in epistemic logics and so forth. But of course, all these are hyperproperties, right? Now, it's not obvious if there's an added value if we go ahead and express these properties in one of our favorite logics, because people who use linearizability know well how to deal with that.
Yes.
But I think there's a certain value in realizing that all these properties have a common basis, and that some of them fall into classes, which mean that they are for comparable complexity sake. So this is something that happened very nicely with HyperLTL, because there are all these many variations of non-interference. And once you formalize them by using quantifiers, you realize that, for all is something different than for all exists. And in fact, of course, the model checking complexity tells you that every such alternation adds an exponent. And then you realize why it is that standard non-interference is cheaper than generalized non-interference, right? It has a quantifier alternation in there. So this kind of standardization of properties, I think, is useful. But what makes it so tricky is that really this is not formal methods, right? You actually have to go out and look at the many hyperproperties that people work with.
Yeah,
and then the setting is not so simple. It's not a finite state model checking problem where you can easily classify things. It's a messy infinite state kind of setting.
Yeah. So when I read actually I heard Fred Schneider talk about hyperproperties back in 2009, 2010, and then I read the paper. It was very exciting. So I looked at the paper, looked at all the classes they had, and said, okay, let me go and see where these appear in the wild. And I spent a lot of time talking to colleagues in system security people, 2012, 2013. And ultimately, I came away with the realization that a lot of it is observational determinism. Like the system security people, everything they write is observational determinism. Like even John Rushby's paper on separability from the early 80s is also observational determinism. And so at that point, then I said, okay, well, then we need better tools to verify that, right? But it's, that was the standard to say that up. And so I do see there are lots of classes, even in the Clarkson-Schneider paper, there were lots of examples of hyperproperties, but it wasn't, not all of them seemed equally relevant or practical. So what I'm trying to get at, I don't believe that that's all there is, right? So there is more, but I just want to get an understanding of like what else is there, and maybe if we can start putting in, like as you said, HyperLTL makes it very clear what the distinction between the classes is, but if we can say, okay, well, this is like plausible deniability. That's a good example of like a real property, which is not just a true safety property, right? And actually, it's got a very good quantitative interpretation as well. So that is an example of like a realistic hyperproperty which falls outside the basic class, right? And so I'm looking for more examples of that. And if we can build up that repository of examples, then I think more people will be motivated to use the logics and develop verification and synthesis and monitoring algorithms for these, right? So anyway, that was sort of the thinking behind my original question.
Sanjit, I completely agree with you. So I had a discussion 3 years ago in a distributed systems conference with a colleague who comes from distributed algorithms. So I was trying to convince her that linearizability is a hyperproperty, and she was not buying it by saying that, well, I can specify linearizability by a set of traces that each of them is linearizable, right? And so that has a recursive definition in it, in the sense that when you say, each trace is linearizable, that has another level of quantification, which makes it a hyperproperty. So, and then I recently listened to another talk, again by a colleague in distributed algorithms, that claimed that linearizability is hypersafety. And of course, the way that we write the formula for linearizability is a for all exist formula, but the inner LTL formula is safety. So they look at the inner part where you could in finite time say, whether this trace is linearizable or not. And then they interpret it as hypersafety, but it doesn't even fit in the definition of hypersafety as is in the original paper by Clarkson Schneider. So I think that document that summarizes, all the examples that at least we have so far in security, in concurrency, in cyber physical systems, in privacy, in causality, in all the things that we have, is very helpful for many reasons. And one of them is there is a document that can point to any of these properties and argue that which class they are in, why it's hyper safety or hyper liveness, or what is the complexity of reasoning about it, or why they are even so the software engineering community has this specification patterns, which are the 54 patterns, which is the gold standard. They are also specified in LTL, and everybody is points to it when it comes to specification, requirement analysis. And I think it will be very helpful to have such document in our community.
Yeah, I agree with that.
Thanks. These are all great points. One last thing I wanted to ask on this topic, and then we have a question from the audience, was on this topic of some classes of hyperproperties maybe not yet studied, but that might be useful to look at. I was wondering, Joe, from your talk, at the end, we had to end pretty abruptly, but you started to talk about some of the notions of trust and how you might encode those as hyperproperties. From the work you've done on that, do you think that existing formalisms would be sufficient for that, or are there aspects of those properties that would make some new formalism or new variant of one of these hyperlogics more suitable?
So I was mostly trying to think of how you could use existing frameworks to model them. And I feel like at least for some simple cases, it looks like the way we are defining trust, it's like a quantitative hyperproperty in the sense that Bernd and Hazem and others have defined. Or you could view it as a probabilistic hyperproperty in PHL or in HyperPCPL. But I think at the core of the question is really there are so many different things that epistemic logics can express. So for example, Bernd mentioned common knowledge, and many of these things are actually hyperproperties. And I think the question there is not so much about the complexity in the temporal aspect of the logic, but in the complexity in expressing the various quantifier alternations. So I guess that is something for us to think about. That, I mean, can we, are there things that hyperproperties cannot express? I mean, is there a case to be made for hyperproperties, right? For things like epistemic logic. So I think, I don't know the answer to that question, but perhaps others in this panel might have thought about this.
I didn't understand that last bit. Because hyperproperties is the universe of properties, right? It captures everything. So maybe there's something that I'm missing. What are you referring to as hyperproperties?
No, that was just a joke. But I mean,
yeah. Sorry.
Yeah.
No, I think I really liked the area that you're pointing us at, right? I think there's a lot of interesting stuff to specify in this area of trust. And the thing that occurred to me when you were speaking is the part that is common amongst these different trust scenarios you presented is that it's basically like relating different evidence pathways, right? So like, there's one agent, multi-agent interaction, that produces some evidence. There's another multi-agent interaction produces other evidence. And then you can think of them as trace fragments. And then your properties are basically relating what happens in all these trace fragments in order to imply some condition on the state of belief or that something will happen. So, I can't say that I understood everything of what you were mentioning in terms of subjective logic and all of that, but there's clearly in this multi-execution type of viewpoint, it does seem like be a good ground for hyperproperties.
Right, and one aspect that we kind of learned during this work on trust is sometimes it's not enough to think about just bounded time horizon properties, but trust is something that evolves over time, right? You have to look at several different fragments of execution to gain. So it's kind of like a continuous learning setup where you're continuously learning something, and that is a thing that has been kind of a niggling doubt in the back of my mind as is that something that's a hyperproperty where you're kind of trying to quantify how your trust in the system evolves over time.
That sounds like a branching time hyperproperty. Is that it? I mean, you're looking at the trust from specific points in time onward, so to speak. Right.
Yeah, so I'm not very familiar with branching time hyperproperties, so perhaps that's something I need to learn about.
No, I mean, so hyper LTL say is a linear time property, right? Or even the Clarkson-Schneider definition is linear time because we only talk about sets of traces, right? And indeed, in many situations, that's not good enough because you want to say the knowledge you have at a certain point in time or the observations you make from some point onward or so.
Yeah.
Right? So and there are various ways how to fix this this root of the analysis. So in logics like hyperQPTL or so, you can just quantify over points in time and then refer to that point in time in the analysis of different traces, say. In logics like hyperCTL star, you can branch into a certain state and then do your analysis from that state onward. Mm-hmm. So I have no idea what would be right in the setting of trust. But it seems to me that you want to compare an analysis that you do at one point of time with the analysis that you may do at a later point in time.
Yeah, that's exactly right. Yeah.
Mm-hmm.
All right, so we have a question from the audience. So let me just read it for everybody. I'm not sure if everyone can see this window. So Bernie says, my understanding is that while self-composition could be used for model checking all hyperproperties, it quickly becomes unsustainable because of state space explosion. Are there any scenarios where it's really applicable besides perhaps K safety for small values of K?
So I think the most common, maybe I can take this opportunity to answer that question and also relate some of our experience with K safety property verification. So I think I interpret small values of K to be 2, K equal to 2, because that's the most common, right? So most of the verifiers are sort of designed to do well at 2 safety. But a few years ago, we were looking at specifying properties relating to the Spectre meltdown style attacks, where you have basically exploits on speculative execution in microprocessors. And we characterized the property of secure speculation as a 4 safety property. So a little bit bigger than 2, but not that much bigger. And so this is described in a CSF 2019 paper. We actually generalized this to something we call trace property dependent observational determinism. So it's observational determinism, but conditioned on another trace property. In this case, the trace property for secure speculation is whether speculation is turned on or off. It's a very simple trace property. And then we developed a verifier based on the simplistic self-composition, 4-way self-composition. It was able to either find exploits in small C programs or prove the absence of them. I mean, these are literally small programs, like 10 lines, 20 lines, that kind of thing. Now, of course, if we want to scale it up, and which we have been trying to do in the last couple of years, this doesn't do so well. So I feel like even even k equal to 2 is challenging in many cases, right? If you apply to real code, k equals 4 becomes more challenging. So my sense in terms of this question, I feel like there's still a lot of work to be done in terms of verifying 2 safety and 4 safety properties of realistic hardware and software systems. I think from a practical perspective, we need even better techniques to do that. And it seems to me there are symmetries to be exploited here, right? So there was, for example, when I was doing work on syntax-guided synthesis a while ago, I felt like there's a lot of scope to apply that to inferring invariance and hyperproperties and hyperproperty verification, because the template for that is often, you're relating like the state of copy 1 with state of copy 2 and so on, right? And in fact, indeed, there was a nice paper, I think either earlier this year or last year by Aarti Gupta and her colleagues on doing exactly that, like using Cygus to synthesize auxiliary invariants for hyperproperty verification, or 2 safety verification, I should say. So anyway, so I think that's maybe a long-winded answer to your question, but I feel like we need more for k equal to 2 and k equal to 3 and k equal to 4.
So I agree with your answer, and I very much agree with the question. So I interpret the question as a statement that self-composition is considered harmful, right? And I think that means if you can avoid it, then avoid it at all costs. So the prime example where people use self-composition and shouldn't are quantitative hyperproperties. For example, quantitative information flow. So the naive way of doing that is, if you want to say that the information flow is limited to n bits, then look at 2 to the power of n different paths and make sure that you can distinguish them. So that of course gets exponential, and there's a straightforward way to avoid that. Rather than look at the self-composition, count the number of different traces. So very often self-composition can be avoided by things like counting. And if you can, you should, because that buys you an exponent or 2 if you can do that. Now, I'm a little bit doubtful if there are that many interesting hyperproperties where you actually need more than 2 traces. But you don't actually scale to k, right? So it's not a real counting problem. So I would be curious to see such properties. I haven't seen that many, but maybe they exist.
All right, thanks, Sanjit and Bernd. Let's see, we have a few minutes left. So another question I wanted to ask about, a little bit related to classes of hyperproperties, maybe not yet so studied, but could be interesting in practice. So someone, I might have been Bernd, I'm not sure, in someone's talk, I don't want to dig back through my notes right now. Somebody mentioned diversity as something you might like in the system. Its behavior should be diverse in some respect. And this, if you formalize this as like some kind of randomness condition, like it should be uniform over the set of behaviors that satisfy some functional specification, for example, then that is clearly a distributional property. It's not a normal trace property. You could think of it as a probabilistic hyperproperty. But at least in the logics that I've seen, I'd have to actually look to see if in, I can't remember the acronym, from Bernd, the logic you talked about earlier today, if you could concisely represent it in that. But in most of the logics that I've seen, you can't say something like, for instance, in some time window, all possible traces within that time window are equally likely. That you'd have to, because you can't quantify over all possible combinations of events in that time. So that could be an example, for instance, of a perfectly natural property to say, I want the behavior of the system to be highly unpredictable, for instance. It's evenly distributed, but that isn't really concisely expressible, I think, in many hyperlogics. So could something like that be an interesting class of of specifications to think about, like diversity or randomness in implementations? Because I think it was in Bernd's talk, you mentioned in randomized algorithms, all the time we have to deliberately put in randomness to make sure we avoid worst case behavior or something like that. Is that a kind of property that we can formalize?
So I can maybe quickly take that. There are, diversity is one. There are even other types of requirements such as, so let's imagine requirements of checking transactions on bank accounts, right? That if you consider each transaction as a different execution, and then you would say that, out of every 5 transactions, I require that any 3 transactions, that the money that you withdraw should sum up to, let's say, $1,000, right? So it's going to be a predicate over the variables of a set of traces, right? So it needs some level of quantification over sets, and we don't have any tools to do that right now. Okay, for any number of traces, and I don't know how many traces are there. I want the sum of transactions to not exceed, let's say $1,000. Of course, you can blow that up to a number of propositions, but that's probably not the right way to do it. There are. So when it comes to data, the relational nature of data among a subset of traces where you don't know how many traces are in that subset is another example of something that we cannot specify with the hyperlogics that we have right now. So I guess I didn't answer your question. I asked another question.
No, it's even better. Anyone else want to comment?
Let me just understand your question really, Daniel. So when you say diversity, you said that, okay, all traces need to be equally probable or so.
Sure.
But isn't it more like in terms of attributes?
Yeah, I just mentioned that for simplicity, but you could imagine something like there's some, you could classify all traces into different groups based on how similar, maybe you have a metric or something, but you say there's kind of neighborhoods of traces and you want to get a close to uniform distribution over that, say. The reason I'm interested in that is I've done some work on randomized synthesis of systems where you need that kind of unpredictability or diversity sort of thing. And we weren't coming at it from a hyperproperty perspective at all. We were looking specifically at, here's the particular property we want, how can we ensure that? But when we were formalizing that, we did think some about, can we capture this in some existing formalism that a synthesis tool could handle? And at the time we concluded no, for this reason mainly, that you could in theory write it as a hyperproperty, but you would have to expand out like all the combinations for the data basically within your time window.
Mm-hmm. Very interesting. Thank you.
So Daniel, just to make sure I understand your question correctly,
yeah.
Isn't the question of diversity kind of related to this notion of epsilon entropy from Kolmogorov? Like there are notions of like epsilon nets on traces that you can place, and you want to make sure.
For sure. There are many definitions of diversity and randomness that people have studied. It's just, I haven't really seen that in the context of hyperproperties in general. Like, is there a hyperlogic where you can concisely write that requirement of having high entropy in some sense, for instance? Okay, well, we're almost out of time. So maybe we'll just close with, are there any open problems? I mean, we've mentioned a whole bunch in the workshop, but are there any open problems that are begging for people to work on that you think is a really exciting area that needs more attention, maybe?
I think I have a boring answer to this. I mean, of course, there are many open problems, but we really haven't solved the problems yet that we have started to solve. So I think, we're really good in inventing new problems and giving bad solutions to them. But for now, the state of things in hyperproperties is still subpar compared to other areas of safety and reliability. So I think we have a lot of catching up to do in terms of scalability and tool support and all these things. So I see a lot of this groundwork ahead of us, which still is super exciting because it hasn't been done before, and it's not obvious how to extend things.
Yeah, And just to add to that, I mean, I think there were open problems, really nice open problems in all the talks today. I just, so, you know, I think there's enough fodder for people to work on, but I'd like to renew my call for trying to compile a list of, you know, practical / real world instances of hyperproperties that we can, you know, show, you know, communicate to the broader community, right? As here are the things where progress is really needed, and have then more people to start to work on these things. Because I feel like the community still is very fixated on K safety for mostly K = 2. And right, and you know, there needs to be work on that from a very practical viewpoint, like in terms of the advances in software model checking that were done 10 years ago, right? A similar thing has to be done for verifying hyperproperties on programs and systems of that scale. But we also need to understand what are the other classes that need more attention.
Thanks. Borzoo or Joe, any last thoughts?
So the first time that I met Bernd was in 2014 in Singapore, and I visited him a couple of months after that. And at that time, so we started working on the complexity of verification of hyper-LTL, and we could hardly come up with, you know, useful, practical formulas that have a lot of quantifier alternations, or, you know, exist for all formulas. And now we have, you know, plenty of those examples over the years, over the past, you know, 6-7 years. So I think, you know, it really benefits us to compile all the things that we have found out, not just algorithmically, but in terms of type of specifications that we can write with hyperproperties.
Yeah, that would be great.
Yeah.
Okay.
Great.
All right. Well, thanks to all of our speakers. Again, we had a great slate of talks and a very interesting panel. We really appreciate all of your time. And thanks to the audience for asking questions and joining us today. We will post the recording online later, at least most of it if we can. And yeah, hopefully we'll stay in touch, and this will inspire some of us to keep working on some of the issues that cross between the different areas that came up today.
Yeah.
All right.
Thank you so much, Daniel, for organizing this with Azim.
Yeah, thank you both. I think this was a great start, and to keep the momentum going.
Yeah.
Thank you.
Thank you.
Bye-bye.
Nice seeing everybody.
Bye-bye.
Bye.